In this last subsection of this unit, and actually the last subsection of our module, I want to show you a trick that uses the facts we learned about the Cartesian trees to finally get to this optimal preprocessing time and space data structure for range minimum queries. And that uses the so-called 4 Russian trick. And at that point, I want to include a little disclaimer or a little, well, rectification if you want. It's about an algorithmic technique that was published in a 2-page paper in the 70s in Russian by Arlazarov, Dinitz, Kronrod, and Farachev. I'm probably not pronouncing them correctly, but I tried. And they all worked in Moscow at the time, but as far as I know, 2 of them are Russian, and the others, at least Dinitz is Israeli. He might have been Russian at the time, I'm not sure. And I didn't find information about the last one, Farachev. It's just not clear if they are Russians. And unfortunately, American authors, ignoring that fact, use this method of 4 Russians nevertheless. And not giving them the honor of mentioning their name is worth enough, but it's also factually wrong because it's probably not 4 Russians. Unfortunately, the name, it got stuck because it was coined at the time when, well, 70s, you remember what happened in history at the time. It's not relevant for algorithms now, but this name is not great, but it's in so wide use now that people kind of gave in and kept using it. I wanted to give this little credit to the original authors, nevertheless, without just mentioning their nationality or their place of work at the time. Okay, first step in this solution, in this more sophisticated solution for the rangemin problem, is taking what we have and see what we can get with simple tricks. Ignore the picture down there for a moment. What we've seen is the sparse table solution is an n log n time and space preprocessing solution that gives you constant query time, but the n log n is not quite as good as we wanted. However, if we apply it to a smaller subproblem, one that has only n divided log n elements, so we apply it to an array of only m elements where m is chosen like that, then m log m, the log n cancels, so that's linear then. So we can apply this simple solution, even though it's suboptimal, we can apply it if we just make our input a tiny tad shorter, a log n factor smaller. We've seen that trick before in Unit 3 when we were talking about parallel processing. Here we'll apply a similar trick, but to use it in a different way. So the first step is we break our array A into blocks of little b elements. And that number is carefully chosen. It will not make sense at this point why exactly it's log n over 4. It will make sense in a couple of slides. For now, what we do is we just break this array into blocks like so. For simplicity, I'll assume that there is no leftover block at the end, but that's a minor detail that you can handle if you want, or you fill your array with elements that are, if it's range min, bigger than all the others, so they never come out as a range min. So that's what you do, and that breaking A into blocks is only conceptual, but we can imagine that it's really consists of little blocks. Here it's 8 elements each. In our example, B is 8. But in general, it should be chosen like this. And now from every of these blocks, you nominate the smallest element and promote it to this small blue array, the B array. To be precise, we don't take the actual value there. Instead, we take the offset inside the block. So in blue here, I noted what is the offset inside the block. And if we know the block ID, so 0, 1, so maybe this is worth pointing out. So that's block 0, right? Maybe obvious, but let me write it down. Block 1, block 2, etc. up to block m-1. If we know the block, we can take that number and multiply with b, so that gives us the first position, and we can add the block local offset, that's the little blue number here. So our array B stores for block 0 what is the offset inside the block of the minimum in that block. So the blue guy is always the smallest elements only inside of this block. Okay? If you want, this is a little rangeman query in itself where we exactly specify one block. Why do we do this? Because B now has exactly the size that's small enough so that we can use the sparse table on it without spoiling the overall preprocessing time or the overall space. B is chosen, or the block size is chosen exactly so that you can take this array B, it's not too long, it's shorter by a log n factor, so you can apply the sparse table technique on it, and we're still within our desired linear preprocessing time and, well, hopefully constant query time. We can do in constant time rangeman queries on this B array. It might just not make too much sense why we want to do this at this stage. Well, we'll come to that on the next slide. The next step here is we have a query that covers a certain range I to j. I drew this here in red, and remember we imagine that our array is broken into blocks like so. How can we make use of the fact that we can use rangeman queries on B to answer this query? Well, first of all, notice that any such query actually covers 3 ranges. There's a certain part here. So this is this prefix. I don't want to use blue for that. So here's a prefix of that block that's covered. Here's a suffix. Sorry, that's the suffix. And here's a prefix of that block that is covered. So we have a part of a block at the end of the query, at the beginning and at the end. But then in the middle, we have a range of blocks, right? So for all but the leftmost and rightmost block, we know that we cover entire blocks. And that is useful because we can find the range minimum in this blue part using only the B array. Because any range minimum in this range will be one of these 3. It can only be a range minimum of a block that becomes the minimum of a range of blocks. Okay, it's a lot of ranges, I know. That's why I warned you up front. So what we do is we divide the query into a constant number of other queries. Remember, this is very similar to what we did for sparse tables. But here we have to be a little smarter in how to do it. We have one large range that scans entire blocks. That's this blue part. And then we have 2 little leftovers, but these are only inside a single block. So I'll call these intra-block queries inside a block and inter-block queries with the spanning blocks. Okay. And now the fun thing happens again if we ask what is the result of the red rangeman query, the entire range. It can only be one of a few isolated points. It can be the minimum in the green range in this suffix of a block, or it can be the minimum in the prefix of a block, or it can be the minimum from the blue range. Now, the example here is a bit misleading. I would have liked to have this minimum outside. So let's suppose this is not here, but instead is here. What I want to stress here is the minimum of this green range need not be a block minimum. And the same for this one. Whereas for the blue ones, we span the entire block, so it can only ever be a block minimum. Now, what is more precisely, what are the 3 ranges? We can express that using other range minimum expressions. So in particular, this first one is that first range min query. It only looks inside this block L. L is defined here, so you can just compute that from the query index. So we look inside one block, and within that block we have a certain range that we span. That's the green part here. We have the second green part down there. It's the same thing, just in a different block and with slightly different indices. And then we have the blue part, and that one's, it looks a bit more complicated, but that's only because this array stores the block local offset and not the actual index. So we take the block offset, that is this expression, and then we add the offset from the block where we find it. So this is, you have to work out this in detail so that it makes sense. This is the block local offset. This is which block turned out to be the minimum, so that gives you the block ID. Maybe this is a good annotation at this point. That's a block ID. That is a block local offset. And from those two things together, you can compute the candidate minimum from the blue range. Okay. So it's not necessarily important that you follow the nitty-gritty details of how the indices are chosen. The important thing here is that you can take your query, the red range again, and you can represent it as 3 different queries. And then the minimum of the entire red range is whatever gives the smallest value from these 3 candidates. So that can be done in constant time if we are able to find these 3 candidates quickly. So that's what's stressed here. If we can compute interblock queries and intra-block queries, then we can compute these red ones. And we only need constant time for that. We compute the candidates. If that's done, we have a set of 3 possible positions in A. So we just look up into A what is the smaller one, and we return that index. And indeed, the blue range we've already solved. That was the previous slide where we discussed that this B is actually small enough so that we can just use sparse tables on it. So that's done. The only thing that's left is the intra-block queries. So we've reduced the entire problem, rangeman queries on a full array. We've reduced that now to only solving the little subproblems in a tiny range, just log n elements at most. It turns out that is the tough part though. And you have to apply a trick to get these. So the intra-block queries remain, and we want this time overall. The challenge is that we have almost as many blocks, so we can really only spend log n time per block. And we can also just spend log n space per block. And we have to be really careful with that. Whereas if we wanted to store the Cartesian tree in a way that it's easy to, well, it doesn't seem possible in an easy way to store the Cartesian tree so that you can find the LCA efficiently. And the trick is we don't have to. So we have many, many blocks, but they're all fairly short, just B numbers. We can also, we also know that we can encode the Cartesian tree for such a small range using 2B bits. And we've counted that the number of different Cartesian trees is not that big. So if we insert what we know about B in here and compute, we find there's only root n different Cartesian trees, even though we have almost n blocks in total. So we have n Cartesian trees in total to store, but only root n are different possibilities exist. So that means many of these Cartesian trees are actually identical. They look exactly the same. So how can we make use of that? And that is what the 4 Russian technique comes down to. We take each subproblem and represent it by its type. So that's a local encoding of the Cartesian tree in our case. And we will use this 2-bit encoding that I've shown you. Then we enumerate all possible subproblem types. There are just root n of those, so we can just pre-compute them all and store them in a big table. And then use the type as a lookup, as an index in that big table. So that's, in a sense, instead of figuring out a smart way how to solve these many instances, we just solve a problem that's simpler because there's few different Cartesian trees in total. There are not so many to choose from, so we can afford to just pre-compute them all. And let's briefly see how this is done. The preprocessing does 2 steps. The first one is for every block we compute the encoding of the Cartesian tree. That is easy to do in linear time. I don't have time in the lecture to show it, but it's actually fairly simple to do it. There's a stack-based algorithm to compute the Cartesian tree, and then a traversal of the tree gives you the encoding. We manually simulated that. And then you use these codes and store them. So you have an array. For each block, you store the code in the Cartesian tree. And the second big thing you do is you store one big lookup table where you have an entry for each block type. So suppose there's one entry, suppose that B is 4. Then we have one entry for this tree. We already know the block type for this tree was 3 1s and 5 0s. That happens to be the encoding of that tree. Remember the clicker question. And then we can we have entries for all possible RMQ queries that are possible inside this tree. So there are actually not so many in this case. I think this should be all. And we can just look up what the numbers are. So this is 0, 1, 2, 3. The arrangement between 0 and 1. 1 is higher, so this is 1. 0, 2, it's 2. 0, 3, it's 2, because that's the root. 1, 2, 2 is the root. Whenever 2 is contained, it's the answer. So it's 2 in almost all cases. That's a fairly boring little example, but that's how it works. And you fill this table for all possible trees of B nodes. You just pre-compute them all and store this in one giant array. Okay. Now, this is good enough because the number of block types, the number of different entries in the first column is only square root n. That's what we just computed. The number of combinations of these columns I and j is b squared, and that's log n roughly. So we have square root n times log squared different rows, and that's a fairly small number. Even if, I don't know, if n is 1,000,000, this is a few thousand. So this is not very big. And we can also compute this efficiently. So with those 2 steps together, we bring down the overall pre-processing time to linear time by, instead of working out how to solve these small instances really, we do an exhaustive lookup table using the fact that there's only few different types. All these little instances of the problem can only be 1 out of square root n different shapes. And so we can afford to pre-compute them all and thereby circumvent the fact that just given the Cartesian tree, it's fairly hard to find lowest common ancestors efficiently. But if we have this lookup table, it's just a lookup. It's just an access in one big array. And putting that all together, I might have lost you in the process, but this is all the ingredients that you need to create a linear time pre-processing, linear space, constant time query data structure for Rangeman queries. And with that, we've also solved the LCE problem in the same space. That was the last big open problem we left in Unit 6. So with that, we've brought the module to a nice conclusion where you've looked into all the black boxes that we used, and they seemed magic at the time. But now you can really look into this and understand the details. It is a bit complicated, I agree. Also to implement it, there's tricks where you can simplify it a bit and compromise on the theoretical guarantees. But the theoretical guarantees are best possible, and this is also a fairly recent result that I like very much. There's some open problems in this area where research is still ongoing, in particular about getting the space usage to the absolute minimum, or avoiding to have access to the array at query time. So a nice little twist on the problem is that you get the array at pre-processing time, but then I'll take the array away from you, and for the queries, you have to work only with your data structure, and you get no further support. You cannot look at the array anymore.